All right, welcome back, everyone. And today we're going to do, again, more ray intersections. We've got two more videos to go. So today we're going to deal with spheres. Spheres are actually considered one of the more simplest things to find intersections for. Normally, they usually teach you that first before they teach you like the planes and things like that. But overall, it's actually quite simple. If you quick image search, you can actually find pretty much a bunch of great images that illustrate the idea behind sphere intersections. Basically, you kind of have three states really. Either you miss, you touch the edge just perfectly, or you have 2 points of intersections. Lighthouse 3D has a pretty good image that kind of illustrates it. Scratcher Pixel has practically similar. They add a couple extra conditions, like having your origin of the ray inside the sphere. That gives you slightly different things. But it's the same idea. You get 2 intersection points, or you get 1 intersection points, or no intersection at all. And the math behind it is very simple. It's these two images illustrate really well. It's really just the use of triangles. It's measuring triangles, and that is really the gist of finding intersection points on a sphere. It's a circle right here, but in practice, it's the exact same thing. So it's not really that a lot of math. It's actually one of the more simplest equations, or the simplest algorithm to understand when it comes to intersection. So since we have a lot of nice flat images to kind of illustrate the idea that we're going to do, these two images pretty much does the trick, right? So we're going to find the point, our center. We're going to project it so we can find this point, which is a TCI. All right, and then once we know this point of intersection, we can test to see if it's inside the circle or inside the sphere. And then from there, we have to then use like the triangle. I think it's Pythagorean theorem. How to measure triangles, and we have 2 out of 3 sides of every triangle, like their sizes. So by using those equations, we can determine the third side of the triangle because of the other 2 sides. Once we project it and we have this length, then we have this length. So that means the only length missing is this one. And once we want to find out the little triangles, we know this length between here and the intersection point of the ray, and we know this length. And why do we know this length? Well, this length right here, the mini triangle within this bigger triangle, it's the radius of the sphere. So if this sphere is 1 unit long, we know the length of this is 1 unit long. We know the length of this. So by using a different, moving the Pythagorean theorem a little bit, we then very easily calculate the third side of the triangle. And that's really, and then once you find the third side of the triangle, then you take this position, you subtract and you add, and you have your 2 points of intersection. And then you just get the whatever one is the minimest, the smallest value, which then means it's the value that you first intersect, and max is the second intersection when the ray is coming out. And this one has from Princeton has a lot more of the formulas to kind of illustrate it. So we're going to step through the code. So now that kind of gave you some generalization idea of how it all works. One thing we're going to have is a new renderable. We have a bounding sphere. So this way we can visually see what our sphere looks like. We've built spheres in the past. I probably did this one slightly different. And that's right. And a sphere, a bounding sphere, is defined by only 2 bits of values. You know, like everything that we do intersection is defined by something. Like a bounding box is defined by minimum and maximum vertices. A plane is defined by direction and a point in space. You know, like everything has some kind of definition behind it. A bounding sphere is defined by a radius and position. That's it. And position we're going to get from our renderable, which has a position value already, and then we have our radius. And I'm caching radius squared because if we're going to do a lot of intersection tests, we need to calculate this often. So might as well just pre-calculate it once, and this way we can always have it for when we want to do intersections. And I'm not gonna, like I said, I'm not gonna really step through this. This is a simple equation of how to make a sphere, and the way I'm doing it is like I'm drawing one circle. I guess let me illustrate. The way I'm building the sphere is actually it's a single line, line strip. So I'm drawing one complete line to build this sphere. So the idea is I go around, and then I go around again, and then I go around again. So this entire sphere is built within a single line call. So I'm going from point all the way across. So if I use line strip, I just have to tell each point, and I just go around, and every time I go around, I just make sure I rotate where my circle axis needs to be. So ideally, you can change the values, like let's say if I want to make this more defined. So I'll say I want seven things. Because right now I set 3, so there's 3 circles. So if I set it for 7, now I got 7 circles being kind of repeated. So by taking this code, you can kind of define how many points, you know, what resolution you want your bounding sphere to be like. They did this right. So, but since, you know, it is a bounding object, it doesn't need to be very complicated. So this is kind of like a low poly, low resolution way to represent where our object is within the bounding sphere. And that's why I use a line strip. So I'm using the least amount of vertices to create a sphere. And it's easier to render a line than to actually an entire mesh. So you can pause, I'll scroll through, or you can get this from GitHub. But that's the gist of how this thing is put together. So, and I have that put into the entity folder. So if I go into here, so we're going to bring in our sphere, make it a global variable called sphere. We set it up, and we set a position because its origin is in the center, so we want it above the grid so we can see it. And so every time you're building bounding stuff like a bounding cube, always make sure you test it not on origin, because sometimes you have to realize you need to bring things into world space. So if you do everything at origin, you might make a mistake, and then when you start moving objects around, things don't work right correctly. So you really should, when you're testing these things or building these type of things, always make sure you move it outside of its local space into some kind of world space. So this way, when you're actually developing these things, you'll catch these errors early on. It's like, why isn't this connecting? Oh, because this is in local space. I need this to be in world space. So you can fix things accordingly. So that's why I usually try to move things away so I can find the errors very quickly. So on camera, we're going to do the same thing we always do. We get our array, and we're going to use our sphere test. So to start off with, we're going to calculate our array normal. Again, this should be done in some kind of array object. In the future lesson, probably in the last video, I'm actually going to start putting together the right way of doing intersections. Like right now, everything is kind of just prototypey, but in the final video, when we're going to do terrain intersections, I'm going to start really building an actual mini simple framework of how to do intersection. So this way you can take all the lessons and then put it back together in the right way, so this can be reusable in your projects. So like I said, that's why I call this a test type of thing. So first thing, we got to find out the direction of our array, and in this case, sometimes we can get away with using the vector length, but to do spheres we need the unit direction, not the vector length. So we need the normalized vector length to do some of the things correctly. So now that we know the array of the direction, we need to find the vector length between the center of the sphere and the start of our array. So if I refresh, if I was going to shoot a ray right through the sphere, that's the first thing we're figuring out. The distance or the vector length between the start and the sphere. And the reason why, like I said, we're going to do that is that now that we have this length, we need to project the length of this line onto our array. So this way we can find the shortest point on our array to the center. So in the shortest point is right here, which is if you do a projection. So that's exactly what the next chunk of code does. Boom. So the projection equation is we're missing the denominator, but in this case we don't need the denominator, because if we do it, I believe with the normalized ray normal, we're gonna get dot over 1, and over 1 is kind of a waste of a division. So you just the numerator is good enough when we're dealing with spheres. So it's kind of why we need it to be normalized. If we don't, then we need to use the division to use the actual vector length of the array. So we can get away with using it normalized to kind of like take away one division. So it's like a more simpler projection example. So by taking the normal direction of our array and then the distance, we are able to get a t projection of it. So we get our t projection, the length of how far we should go. We get the array normal, we clone it, we scale it, and then we add the start. We're going to visualize the point, and we're going to visualize a line. So if I go, refresh, if I go there, and there it is. There is the length of the gray line, the distance, the vector length between sphere and origin projected onto array. Now, like in these these images, that's what like this green line is, or that gray line is. We're building this whole giant triangle. Oops. So we got to build that whole giant triangle. Now that we got this, we're going to test to see this length. Because if this length is within the radius of the sphere, that means the ray does touch the sphere at some point. Else, if the length is too far, let's say if I shoot the ray here, so this length should be greater than the radius. That means there's no intersection. So that's the next step. We need to find how long this length is. Now, there's two ways to determine this length. One way, which we've been doing in previous videos, is we create the vector length of this line. So we take this point minus that point, and then we do like a dot product on it, onto itself. This gives us its length squared. And then we can just compare it with the radius squared, and that calls it a day. But that requires us to determine this t position on the array. So if we want to save time and not determine this t position, we can use the Pythagorean theorem to determine the length of this line. So the length, so since we know this length, right, And our T projection is this length, is the length that we need to travel on the normalized to get here. So we know this length. So by knowing the lengths of two sides of a triangle, we can very easily determine the third side of the triangle. So, and that's what we're going to do here. So this is the Pythagorean theorem. To me, it's like a tongue twister. So we have adjacent squared plus opposite squared equals hypotenuse squared. This is the hypothesis. Yes, hypotenuse. And this line is the adjacent. So we know the adjacent and we know the hypotenuse. I suck. So we know these two sides. So if we rearrange the equation and subtract the adjacent to the other side, we know that the opposite squared equals hypotenuse squared minus adjacent squared. And that's what we got here. So right to center is this gray line, and then T projection is this. So if we subtract the other, we get the opposite length squared, the final value we want. Now, in our console log, I'm outputting the values so I can actually see what they look like. But I'm also showing you the way we normally do it. We have IPose. You know, we make a copy of it, and then we subtract the sphere's position, and then we do a square magnitude. Or we can just take this value and then say dot twice, because they create the exact same thing. But since the vec3 already has a function that squares itself, basically, and it does a dot product on itself to get it the square magnitude, so we can just call it right there. Makes things easier. But that's if we want to calculate IPose. So if you, like I said, if you want to avoid this extra step, if we don't need to, we can just do this. We just do two sets of multiplication and we're done. Instead of doing a subtraction and then we have to do, let's see, we have to do a multiplication, an addition, and then we have to do another subtraction, and then then another dot product. So it actually takes extra steps to get an IPose. To do this, it takes more math operations to get the same value. But you'll see in the console, we get the exact same value no matter which direction we go. So if I click here, so by using the shortcut, we get the exact same value by doing it the other way. So triangles are very important. It helps you, it shortens sometimes your code if you know these equations, which I don't. So I had to read a lot of tutorials, and like I said, I haven't been in high school in a long time, and I haven't taken geometry in a very long time. And pre-calc or trigonometry is also the study of triangles. So there you go. So now we know this length, we know this length, we know this length. Now if this is 1.16 and it's less than 1.25. Now our radius is 0.5 because this is a unit sphere. It's one unit in diameter. But we square it, so that's the square value. And the reason why we're using the square values as opposed to the actual lengths, instead of using like opposite length and radius, is that to get opposite length, I actually need to take this value and do the square root of it. Square roots, are one of those operations that's slower on the CPU compared to anything else. So it's actually just easier to, it's quicker CPU-wise to, again, do like a dot product on itself than to do a square root on that value. And that's why I said we should cache the radius squared, so this way we can then, we already have this value, we won't want to compare it when we're like doing like a bunch of spheres and we're doing in a loop. So having that cached would save us one math operation. The only operation we have to do is a memory lookup. So we're going to have two if conditions. If the length squared is greater than the radius squared, and then it's outside the radius. It's no intersection. We return null. If for some reason, rare case, but it can happen, if the length is equal to square, it's a single point intersection, and we bring IPOs, and that's it. And we have that position. Now we have O length. Now, what we do now that we got this big giant triangle, we need to find these 2 points of intersection, right? Because it's inside the circle. So let's say, let me shoot the ray this way. So this point is not the real T position. It's not the on the ray because it's inside a circle. So what we want is here, around here, and around here. So those are the 2 points of intersection. That's what we need to find out. And well, this one's a bigger image, 800 by 600. So, like I said, that's what we need to figure out. Since we have this big triangle already, now we can just have to determine the shorter triangle. And we already have the distance. We already pre-calculated. It's T projection squared. And now we know this length because it's the radius of our sphere, because it touches the circle itself. So by rearranging the Pythagorean theorem, we can then get this length as well. And so let's see. And we can get that done right here. So we have opposite length. So we're going to take the hypotenuse, which is the radius squared. And we already have the opposite, even though I call it opposite, and I think I rearranged it to adjacent. The adjacent and opposite names can change based on how the triangle is set up, but the hypotenuse is always the longest side. So we got that squared, and then we have to do the square root because we need the actual full length. So at this point, we need to do a square root. There's no way around it. So once we have O length, right, and then we go to the final step. So O length, subtract or add to our original intersection point. Like I said, this point right here, we add to it, which would take us over here, and if we subtract to it, it takes us over here. And so we get our new 2 T values, and then we just check to see if one's bigger than the other. So if T max is less than T min, which I probably should have done it, called it. It makes more sense. Like our other videos, we call it T max, T min, I think. So if they, for some reason they are like that, we swap them, and then we just visualize it. So refresh. I shoot a ray right through it, and there you go. There's our 2 points of intersection. And green one is always the one that's closest to the origin. It's our T min. So I can shoot this as many times as I want. And we always get that perfect spot. If I shoot it outside, that's it. We don't even, the function doesn't go any further because it's outside the sphere. And even this still works, even though it's like almost like perfectly a circle. Or it goes right through the north and south polar things. And that's it. And that is how you do a sphere intersection. And like, I don't want to leave you guys with like all that messy ass code. So we're going to give you a cleaned up version that gets rid of IPOs and everything else. So like I said, we got all the math. We got array, we got our center, we got our projection. 3 lines of code, we're done. Once we have our projection, we're going to do our test. If it's inside the sphere, we're going to calculate its 2 points of intersection, swap, and then we have our ipose. And same thing here. If it equals, we create our ipose right on the return. So this we always get the ipose at the very end. So we click refresh. There you go. We got our point of intersection marked with the black line, black circle. So you always got to test the weirdest things, because sometimes you never know. There's always like an exception to the rule. So no matter which direction I shoot the sphere at or which angle, I always get it. And if I click out, nothing. I got a nice error says no intersection. We're good. And that is a sphere intersection ray test, or ray sphere intersection test. So that is it. So hopefully that was a short one. We're going to revisit spheres in the next lesson. Next lesson, we're going to do capsules. And a capsule is a complex object of intersection, because it's actually 2 objects in one. So it's a cylinder and it's a sphere. So that's why we're going to do capsules. Capsules is like one of the last more complicated things. And capsules are used a lot in Unity. I don't know Unreal very well. But Unity, you do use capsules a lot. Sometimes the capsule boundary is used for like user characters. Like, if you put like that around a character, and that's how you use them to move around the world. That's kind of like their physics object. That that, like if a character's walking on terrain, you use that capsule bounding to actually test it. Compared to the ground, so in relation to it, usually in physics, if you want to shoot things at it and jump and whatever. So I'm gonna do capsules. Capsules significantly because there's actually like no videos or no tutorials on capsules themselves. So I think it's very important that we cover that one, because like I said, it's a very useful object in Unreal, not in Unity, and really no one really talks about how to implement it. So I'll talk more about that in the next lesson. So that's going to be the next video. I have it all done. It works. It took like several days to get it working right, but it's working, so it's good. So I got to find time to record that video. And then I'm almost done doing terrain intersections, and that should end our intersection videos. And then we would probably go back to animations. And I'm actually going to start exploring voxels as well, along with amateur animations. So I got some cool projects I want to start doing, and it's going to be part of the videos. So you guys might get really kick out of the voxel idea. I stopped my floor plan application because I saw something that's similar to the floor plan project that I used for a couple of videos. That kind of started the intersection video. So with all these new intersection functionality, it's gonna be useful, very useful in the next project. It's going to be kind of like a level builder, but it's the Portals 2 level builder. If you look, I forget what it's called, but if you look up the Portals 2 level builder, we're going to try to rebuild that in WebGL. That looks like awesome. That's going to be fun. So all this intersection stuff is going to be reused for that little project, and that project is going to require intersections and voxels. So that's what's going to happen hopefully in the near future. So I'm going to try to bounce back and forth between amateurs and voxels, and the Portals 2 level editor. Look it up. It looks really awesome, and hopefully we get to rebuild some of it in WebGL. So like and subscribe. And got any questions? Ask away. Comments, whatever. Just ask away. I'm here. And see you guys at the next lesson.